Today, we are undertaking a pretty critical mission. We're flying to the far north, a place defined by its stability in ice, which is now rapidly becoming, well, the largest climate wildcard on the planet.
We are talking about the warming Arctic, and specifically, that potent greenhouse gas time bomb buried right beneath the frozen ground, methane, or CH4, trapped in the permafrost.
Exactly.
The mission seems simple on paper, but is, incredibly complex in reality
Yeah,
to quantify this massive, uncertain threat.
it is. This is a deep dive into the complex science and really the incredible arsenal of high-tech gear that scientists are using. We're talking lasers, specialized gliders, deep learning AI.
They're essentially high-stakes methane detectives.
That's a great way to put it. They're mapping and measuring this changing landscape.
Mm.
We have to understand not just what is happening, but how you even begin to measure something so vast and so fundamentally unpredictable.
Okay, so to set the scene for everyone, let's just define permafrost. Most people know it's frozen ground, but what's its scale? What is its significance when we talk about carbon?
Well, permafrost is ground that remains frozen year-round, and it covers an astonishing 22% of the northern hemisphere land area.
22%.
It is an area that spans Siberia, Alaska, Canada, parts of Europe. And it's a mix of soil, rock, ice, and crucially organic material.
Right, the remnants of ancient life.
Exactly. Plants, animals, all of it locked away by the cold for millennia. The critical and frankly alarming fact is that this permafrost layer holds about twice as much carbon as is currently circulating in the Earth's entire atmosphere.
Twice the atmospheric carbon. That's
Yeah.
that's like a massive bank account of frozen potential emissions just waiting for an overdraft.
Precisely. And observations confirm that this bank is failing. The permafrost is rapidly warming, and it's already releasing thawed carbon as both CO2 and methane.
So how bad is it right now?
If we look at the current global warming level, which is, approximately 1.2 degrees Celsius above pre-industrial levels, we are already committed to losing roughly 25% of the surface permafrost,
Even if we stopped all emissions today.
even if we stop today.
So a quarter of that massive frozen bank is already destabilized no matter what we do now.
That is the implication of our current warming trajectory. And the climate forcing, the warming effect resulting from this thaw could eventually be as large as that of a major global emitting nation.
A whole country's worth of
A
emissions.
major one. And this feedback just fundamentally complicates our ability to meet international climate goals because it's an emission source we trigger, but one we can't directly control.
Okay, let's unpack this, starting with why methane CH4 is the ultimate wild card in this planetary game, and why it demands this high-tech detection effort.
Mm.
When we talk about climate change and emissions, carbon dioxide, CO2, it just dominates the conversation. It's the sheer volume that matters. But methane, while there's much less of it, packs this immediate, powerful punch. How should we contrast CH4 and CO2 for you, the listener?
Well, we can think of CO2 as a marathon runner. It stays in the atmosphere for centuries, exerting a long, steady pressure.
Okay.
Methane, however, is a sprinter. It's much shorter lived. It only lasts about 10 to 12 years on average before it breaks down. But during those 12 years, it traps an absolutely astonishing amount of heat.
What does that mean in terms of warming power? I've seen the numbers, and they're always shocking.
They are. If you look at the standard metric that's used for near-term impact, the global warming potential over a 20-year time frame, methane traps 86 times as much heat as carbon dioxide.
86 times.
Yeah.
Okay, that explains why, despite being responsible for only about a quarter of total atmospheric warming to date, addressing methane is considered the most immediate lever we have to slow warming in the near future.
Absolutely. And that high potency is exactly why the current situation in the Arctic is so worrying. I mean, while the increases in CO2 are problematic, they are generally conforming to scientific expectations based on industrial activity.
We kind of know where they're coming from.
We do. Methane, however, is not. Since about 2006, methane levels have been climbing much more steeply than climate experts anticipated.
So that sounds like a fundamental challenge to our understanding of the current system. It's a real mystery.
It is a scientific mystery, but one with massive policy implications. The degree of growth in atmospheric methane was so unexpected. I mean, the source material points out it was not even considered in the pathway models that were preparatory to the Paris Agreement.
The very models that set our climate targets.
The very same ones. Those models set the budget for how much CO2 humanity could emit to stay within 1.5 or 2 degrees Celsius.
So if those initial climate budgets failed to fully account for this surge in methane, which is, again, 86 times more potent in the short term, How significantly does that change the scale of the challenge we face today?
It means the challenge is steeper. It means the margin for error is slimmer. We are trying to find the source of that abrupt surge. And while the long-term rise over the last 40 years is best explained by human activities, the mechanics of thawing permafrost represent a huge source of uncertainty that complicates any budget calculation.
Which brings us to the core challenge in predicting the future of permafrost. The difference between two kinds of thaw, one that models can handle and one that is, well, nonlinear and explosive.
Exactly. The initial challenge of prediction stems from a major modeling gap. Historically, most Earth system models, or ESMs, they've simulated permafrost thaw by focusing on gradual, linear, top-down processes.
So you mean like an ice cube just slowly melting from the top down year after year?
That's a perfect analogy. That's gradual thaw.
And then we introduce abrupt thaw, which sounds much more like something out of an environmental disaster movie.
And it kind of is. It's a nonlinear process that results in a fundamentally faster and more widespread degradation. Abrupt thaw includes catastrophic phenomena like thermokarst.
Can you break that down for us?
Sure, thermokarst isn't just gradual melting, it's when the ice wedges that hold the very structure of the soil together melt, causing the ground to rapidly collapse. You also see hill slope collapses and the deepening impact of intensifying wildfires, which burn away the insulating surface vegetation.
I've seen the images of thermokarst collapse, these giant gaping pits forming in the tundra. They're stark. What's the implication of leaving this nonlinear, dramatic process out of the primary climate models that we use for policy guidance? Is that a minor oversight?
It is far from minor, and this is probably the most critical point for you, the listener, to grasp. While abrupt thaw may only affect about 20% of the northern permafrost region spatially.
Okay, a fifth of the area.
Right, but it contains at least 50% of the entire permafrost carbon pool.
Wait, say that again? A fifth of the land holds half of the carbon.
At least half. That's because the ice-rich deposits that cause the most dramatic collapse tend to be where the deepest, oldest carbon is stored.
So to ignore that process is to fundamentally misunderstand the feedback loop.
It is a critical omission. The source material emphasizes that the underrepresentation of these nonlinear, high-impact contributions in models that inform climate policies, well, it compromises the ability to achieve targets like the Paris Agreement's 1.5 or 2-degree limits.
We are essentially running the climate race with an incomplete map of the track.
That's a very good way to put it.
And this collapse isn't just happening on land, right?
Yeah.
The edges of the Arctic are being eaten away by the sea, which is speeding up the carbon release along the coasts.
That's the coastal threat. Along the Arctic coast, the erosion is intense. You have waves combined with warmer temperatures that soften the frozen coastline, and they are actively removing material from the permafrost.
At what rate?
The retraction rate is currently around 0.5 meter of coast lost per year, but projections suggest that rate is likely to double or even triple by the end of the century.
That scale of loss is catastrophic for any communities or infrastructure along the coast, obviously. But what happens to all that eroded carbon?
It washes into the ocean, where the organic material decomposes. And this decomposition is a major issue because it increases the CO2 content in the surface water of the ocean.
Which creates a secondary problem.
A secondary global-scale impact, yes. It slows down the ocean's natural ability to absorb CO2 from the atmosphere.
Wait, so the carbon released from the thawing land doesn't just release its own CO2 and methane, it actively makes the oceans less effective at cleaning up our atmospheric CO2. That's a terrible double whammy.
It is, exactly. The source material indicates that if this coastal erosion process is properly considered, the inner Arctic Ocean could absorb between 9 and 19% less atmospheric CO2. It significantly reduces the efficiency of the ocean's carbon pump.
And I'm guessing it harms marine life too.
Of course. The increasing CO2 content in the seawater due to this erosion also pushes the ocean towards greater acidity, which stresses and threatens the entire regional marine ecosystem.
And we also need to briefly touch on the area that represents perhaps the deepest scientific unknown, which is the subsea permafrost.
Right. Subsea permafrost is the permafrost thawing beneath the ocean floor. It's often remnants of the last ice age when the continental shelf was dry land.
That's a huge flooded area.
The vast area, yes. And research here is much newer, but it potentially contains massive stores of methane hydrates, these ice-like structures that hold methane molecules.
And what's the verdict on the threat from those?
Well, the scientific consensus is still coalescing on the immediate threat. but there is strong evidence it's a vital component of the Arctic climate system. It requires urgent monitoring because its thaw could push the climate past further critical tipping points due to massive methane releases.
That gives us a pretty sobering picture of the scale and the catastrophic mechanics of the thaw. Now, let's move into the messy scientific details of what exactly happens biogeochemically when the ground thaws, which leads us to a fascinating scientific contradiction. Section 2 is where the conventional climate logic really starts to break down, and we enter what we've dubbed the hydrological paradox. For decades, the primary question for carbon release in the Arctic has been pretty straightforward. Does the region get wetter or drier? And that matters because of the gas that gets produced.
That's right. The traditional simple logic relates directly to oxygen availability. When soils are wet, they become anaerobic. Oxygen is absent or rare. And microorganisms, in the process of decomposing organic material without oxygen, produce methane, CH4.
Okay.
Conversely, when soils are dry, they are aerobic, meaning oxygen is present, and the decomposition produces carbon dioxide, CO2.
So, simple summary. Wetter ground means more of the potent methane, drier ground means less potent CO2.
If the Arctic were a simple flat sponge, that would hold true. But what models now show is a fundamental conflict.
How so?
Well, simulations with sophisticated Earth system models, like the MPI-ESM, they do predict increasing precipitation for the region in the future, which suggests a wetter climate overall. But here's the paradox. The thawing of the permafrost allows water to drain away more easily through newly opened subsurface channels. This effectively lowers the water table and causes the soil surface to dry out in the long term.
So the region gets more rain, but the ground retains less of it. It's a conflict between increased inputs and radically increased drainage capacity.
Precisely. And this draining-related drying doesn't necessarily lead to the expected reduction in methane. This is where the simple wet-dry logic is completely overturned.
That sounds completely counterintuitive. How can a drier Arctic still lead to increased methane production?
Researchers, using that coupled climate model, the MPI-ESM, they uncovered a specific chain of events, a paradoxical feedback loop that overrides the simple moisture control.
Okay, let's walk through it step by step.
Okay, let's go. First, less soil moisture leads to fewer clouds forming locally.
Right. Less water evaporating, fewer clouds. Makes sense.
Secondly, fewer clouds allow more intense solar radiation to reach the land surface, which significantly amplifies local warming. This heat, thirdly, stimulates plant growth. The plants thrive in the warmer, drier conditions.
So warming, driven by less cloud cover, leads to a thriving ecosystem on the surface.
Exactly. And that thriving ecosystem provides more substrate, more dead plant material for the microorganisms underneath, even if the soil is slightly drier than it was previously.
So you're giving them more food.
You're giving them more food. And that enhanced microbial activity, working on a larger food source, surprisingly increases overall methane production.
That's incredible. The simple prediction that methane fluxes increase in a wet Arctic and decrease in a dry Arctic is incorrect, because the indirect effects of warming and enhanced plant productivity completely overturn the direct moisture control.
It's a perfect illustration of why the Arctic is so difficult to model. It's not a single factor, it's the complex interaction between hydrology, cloud cover, and biology.
Do we have real-world data to back up this counterintuitive finding? I know we looked at a specific drainage experiment.
We do, yes. The complexity revealed by the models is confirmed by real-world manipulation studies. A significant study focused on wet tussock tundra near Chersky in northeast Siberia. They intentionally introduced a long-term drainage disturbance, essentially lowering the water table to mimic the effects of thawing permafrost.
What were the direct effects of that manipulation? What happened?
The artificially lowered water table depth almost halved the CH4 emissions, which, initially validates the moisture control idea.
Okay, so drier did mean less methane at first.
At first. But the fascinating nuance is what else changed. The drain site showed enhanced carbon turnover. Both ecosystem respiration, so carbon leaving the soil and grows primary production, plant growth, were consistently higher compared to the control site.
So the whole system just became more active and more responsive.
Precisely. And critically, the drain site became more sensitive to deep soil temperatures for its CH4 emissions. It fundamentally changed the ecosystem's response profile.
So while drainage reduced methane initially by drawing down the water table, it also primed the ecosystem for rapid carbon cycling and made it more susceptible to releasing methane from deeper layers when warming occurs.
Exactly. The complexity necessitates continuous high-resolution measurement.
This complexity is also why we need to focus on seasons we usually overlook. The focus is always on the brief summer growing season. But the Arctic's winter is proving to be a massive and surprising methane source.
Indeed. Historically, logistics have limited long-term studies covering the cold, snow-covered seasons. It's difficult and it's expensive to keep equipment running in a deep Arctic winter.
I can imagine.
But the observational data we now have reveals a profound finding. Cold season emissions, spanning the 8 or 9 months from September to May, account for at least 50% of the annual CH4 flux.
Half the annual flux happening when everything is supposed to be dormant or frozen solid.
Yeah.
That genuinely feels like a narrative-breaking moment in climate science. How long have scientists known this, and why was it missed for so long?
It has been confirmed only relatively recently, largely due to the deployment of continuous autonomous monitoring systems that can survive the winter, which is a technological feat in itself. It was missed because the fluxes are low relative to the summer peak, but they occur over a vastly longer period.
Yeah, how does the physical mechanism work? If the ground is freezing, shouldn't that lock the gases in?
The process is tied to the transition period, specifically what's called the zero curtain period, which often happens around October and November. This is when the soil temperature hovers right around freezing, 0 degrees Celsius.
Okay.
During the growing season, methane accumulates in the unfrozen pockets of soil. As the soil starts to freeze, the expanding ice crystals physically push the dissolved gases, both CH4 and CO2, out of the water and soil pores, forcing them upward and releasing them in these significant bursts.
So the soil essentially acts like a carbon soda bottle that traps and pressurizes the gas during the summer, and then it pops its top when it freezes.
That's a great analogy. In a study from Zackenberg, northeast Greenland, the accumulated emission during these freeze-in CH4 bursts was found to be comparable in size to the entire growing season's emissions in certain years.
The whole summer's worth in just that one burst.
In some years, yes. And it often accounted for a large fraction in subsequent years. This non-growing season flux is a major and previously underestimated contribution to the annual carbon budget. If you are only measuring methane in July, you are missing half the story.
Now let's talk about a spatially limited Arctic process having a massive global impact. This is the concept of teleconnections, where the Arctic's fate influences the world's largest methane source near the equator.
Right, this connects back to our hydrological paradox discussion about cloud cover and local warming. Earth system models have uncovered a really far-reaching consequence. If Arctic cloud cover decreases and the high latitudes heat up faster, which is the observed trend, it decreases the temperature gradient.
The difference in temperature, you mean?
The difference in temperature between the tropics and the Arctic, yes.
And why does that temperature difference matter for global weather patterns?
Well, that gradient is a major driver of global atmospheric circulation, specifically the jet stream, and the overall speed of the global conveyor belt of weather. A decreased gradient shifts atmospheric steering patterns, and this shift could significantly affect precipitation patterns near the equator.
And the consequence of changing precipitation in the tropics.
It likely affects tropical wetlands, which are the world's largest natural source of methane.
Precisely. Tropical wetlands contribute about 30% of total global emissions today. So if Arctic climate shifts amplify that source by altering tropical rainfall-making regions wetter or drier in unexpected ways, the resulting global methane impact accelerates dramatically. Wait, so let me get this straight. If we fail to control warming in the Arctic, we are essentially making the world's largest natural methane source, the tropics, even worse. How confident are scientists in that link? Is that a consensus view or is that a radical prediction?
It's a profound realization that's emerging from comprehensive Earth system modeling, specifically the coupling of atmosphere and soil processes. While the exact magnitude is still subject to model uncertainty, the mechanism itself, the change in large-scale atmospheric patterns due to reduced Arctic tropical temperature contrast, is physically sound.
This is not a wild theory.
No. It means a process that seems localized in the high north could have just astonishingly far-reaching consequences for global tropical methane sources.
The scientific picture we have just painted is one of immense complexity. Nonlinear thaw, half the emissions happening in winter, and contradictory hydrology. We can't rely on simple estimates. We need, well, forensic science and advanced technology to precisely sniff out where the methane is coming from, its quantity and its origins.
Exactly.
We'll start with the ground-based monitoring, the foundation of the so-called bottom-up approach.
The bottom-up approach is all about getting actual measurements of fluxes, the physical exchange of methane between the surface and the atmosphere. And scientists use a tiered system. On the smallest scale, they use what are called flux chambers.
What are those?
They're essentially small, automated, upside-down buckets that measure gas exchange over maybe a square meter of ground. They give us very local, direct rates of emission.
Okay, and then we scale up from the chamber.
Correct. Then we step up to eddy covariance stations, which are far more sophisticated. These are towers that use highly precise instruments and lasers to measure atmospheric turbulence and gas concentrations in the air as it passes over.
So they're sampling a much bigger area.
A much larger footprint, yes. Ranging from tens of square meters up to several thousands of square meters, they are absolutely essential for understanding local ecosystem fluxes.
These eddy covariance towers are the backbone of local carbon monitoring. But the permafrost region is gigantic. I have to assume there are major gaps in coverage, particularly in remote Russian and Canadian territories.
There are significant gaps, yes, particularly in the most remote areas that are currently undergoing the fastest changes. And that's why major collaborative initiatives are so crucial. One key effort is the Permafrost Pathways Project, which is led by the Woodwell Climate Research Center.
And what are they doing to fill those gaps?
They're tackling them by synthesizing all available fragmented data into the Arctic Boreal Carbon Flex database, which is now in version 2.
So they're taking scattered data and integrating it for a unified picture.
Exactly. And critically, they are actively installing new eddy covariance towers in critically undersampled regions of the permafrost zone. These new ground measurements are vital because they provide the necessary truth data to validate and train the regional climate models and the satellite measurements.
Speaking of forensic science, one of the most powerful tools in this kit isn't measuring the quantity of methane, but using isotopes to fingerprint the type of source. Why are isotopic signatures so powerful for a methane detective?
It's the ultimate forensic tool. Methane from different sources, say a microbial source like a cow or a wetland, versus an ancient geological source like a fossil fuel leak, has a distinct isotopic signature.
A chemical fingerprint.
A chemical fingerprint. We measure stable isotopes, specifically DCCH and DCH. These track the ratio of heavier isotopes, carbon-13 and deuterium, to the lighter, more common isotopes.
And this allows scientists to essentially DNA fingerprint the gas and trace it back to its origin.
That's the idea. By measuring these ratios in the atmospheric background, scientists can test hypotheses about where the recent sharp atmospheric increase is originating.
So what have they found?
For instance, the recent surge since 2006 is characterized by an isotopically lighter signature. This suggests that the primary driver of the uptick is biogenic, likely from wetlands or agriculture, rather than a geologically heavier fossil fuel source, which is often depleted of the lighter isotopes.
But the sources also provided a crucial nuance here. Even if fossil fuels aren't the primary driver of the recent spike, they're a much bigger problem overall than we thought.
That's a key refinement in our understanding. Isotopic studies, including those using highly accurate data, found that global fossil fuel methane emissions were actually at least 60% greater than previous best estimates.
60%.
At least. So while they might not be driving the current acceleration spike, their overall contribution to the total methane pool is vast and requires immediate mitigation.
Tell us about the specialized equipment required to perform this forensic analysis, because sampling trace gases in remote locations and analyzing their isotopes sounds incredibly technical.
It requires extreme precision. The INSTAR Stable Isotope Lab at the University of Colorado Boulder is a global leader, and they maintain the largest data set of stable isotopes in the world in collaboration with NOAA.
Right.
Since methane is a trace gas, meaning there isn't enough in a standard air sample flask to measure conventionally, they have to concentrate and separate it.
So how do they handle such small trace amounts?
They rely on continuous flow systems. The air sample moves on a stream of helium gas. It is then cryo-focused, meaning it's trapped and concentrated using extremely cold temperatures.
Wow.
Then it's separated on a gas chromatography column, which acts like a microscopic chemical highway, separating the CH4 from all the other components in the air. Finally, the isolated methane is combusted into CO2 and measured in a mass spectrometer.
That is a complex process.
It is. It's the only way to get the signal-to-noise ratio required to confidently fingerprint the source.
That is forensic climate science. Now, how do we get those samples over the vast, remote, and often hostile Arctic terrain? We need a system that bridges the resolution gap between the small local ground stations and the huge satellite view.
And that is the role of airborne measurement. Airborne eddy covariance measurements are essential because they provide spatially resolved turbulent fluxes. They can tell us not just the concentration of methane in the air, but the direction and rate of its exchange with the surface below.
What platforms are robust enough to fly these instruments regularly across the Arctic?
The NOAA Global Monitoring Lab, in collaboration with the U.S. Coast Guard, conducts biweekly Arctic Domain Awareness, or ADA, flights. They use Workhorse Hercules C-130 aircraft, flying long routes from Kodiak up to Barrow, Alaska, from March to November.
That's a massive logistical commitment. What are they measuring on board?
They are collecting air samples in flask for later lab analysis, but they also rely heavily on continuous, real-time measurements using specialized instruments called CRDS analyzers, cavity ring-down spectroscopy analyzers.
What do those do?
These instruments use highly stable lasers bounced between mirrors in a chamber to measure CO2, CH4, CO, and H2O.
And why are these CRDS analyzers so important?
Well, they provide extremely stable and precise measurements with an estimated uncertainty for CH4 around 1.4 parts per billion. That level of accuracy is critical because the instruments are autonomous and robust enough to maintain stability despite the huge variations in pressure and temperature encountered during a long flight.
So they can pick up a tiny signal from miles away.
They can isolate a methane pulse caused by a specific local event, even from a plane flying miles above, yes.
Beyond military-grade transport planes, I understand researchers are also adapting smaller, highly maneuverable platforms to get closer to the surface.
Yes, motorized gliders are a fascinating adaptation. Platforms like the ASK-16 Touring Motor Glider are equipped with specialized probes to measure 3D wind vectors, along with those CRDS gas analyzers.
Why a glider?
A glider is ideal because it can fly slowly and low to the ground, mapping turbulent fluxes over heterogeneous landscapes without disrupting the airflow as much as a large jet. This gives them the high spatial resolution needed to differentiate between a methane spike coming from a small lake versus a larger wetland.
And finally, let's mention NASA's efforts to translate this air data back to specific locations on the ground across the huge Alaskan landscape.
The NASA Carbon and Arctic Reservoirs Vulnerability Experiment, or CARVE, was instrumental in this. They realized that simply collecting air data wasn't enough. They needed to know exactly where that air sample had originated on the ground. So they used advanced atmospheric transport models, specifically the Weather Research and Forecasting Model, WRF, coupled with the stochastic time inverted Lagrangian transport model, STILT.
What's the benefit of combining those models to generate a footprint?
The footprint tells you the probability distribution of where the gas in your air sample came from. By running the WRF STILT modeling, they generated high-quality surface influence footprints on a very detailed grid 0.1 degree resolution, or about 3.3 kilometer spacing.
And that detail helped a lot.
It dramatically improved their flex estimates across the highly heterogeneous Alaskan landscape. It allowed them to better link the atmospheric measurements back to specific ecosystem types, confirming which ecosystems, like bogs or collapsing slopes, were the dominant emitters.
We've established the local view from towers, the regional bridge from aircraft, but to truly map the pan-Arctic threat, we need the ultimate top-down perspective from space. But satellites face unique obstacles when trying to peer down at the poles.
They do. The Arctic is incredibly challenging for satellites that rely on measuring reflected sunlight. While instruments like Sentinel-5P TROPIMI and GHG-SAT successfully detect CH4 concentrations globally, the Arctic presents three main limitations.
What are they?
First, the orbital geometry and the sheer geography make data collection difficult. Second, there are no dedicated permafrost monitoring missions, nor are there satellites designed to dwell over the Arctic in a highly elliptical orbit.
And the third limitation involves the sun and the ground itself.
Yes. For much of the year, there is limited sunlight, and the sun angle is always low. Solar reflectance spectroscopy sensors struggle under these conditions. Plus, you have seasonal factors like persistent snow cover that interfere with the measurement.
It just looks like a bright white blanket to the satellite.
Exactly. It obscures the subtle changes on the ground.
So, if the top-down view is inherently limited, how do scientists ensure that data is useful and accurate?
The key capability and the focus of immense technological effort is cross-calibration, or what they call ground truthing. This absolutely requires simultaneous top-down satellite measurements and bottom-up ground sensor measurements.
You have to measure the same spot at the same time.
Ideally, yes. A mobile ground sensor would be placed directly along the satellite's path as it passes overhead. This simultaneous data collection allows researchers to integrate the data for regional scale analysis, significantly improving quality and confidence in the satellite's readings.
Remote sensing isn't just about detecting the gas itself. It's also about seeing the physical change in the landscape, which is crucial for inputting into the next generation of models. What non-gas monitoring work are satellites doing?
Satellites are vital for monitoring the physical degradation necessary for predicting future emissions. Researchers are mapping dynamic changes like intense wildfires and critically retrogressive thaw slumps, that landscape collapse we discussed earlier, a rapid form of thermokarst.
How do they map something that complex, often hidden by cloud or snow, over such a vast area?
They are leveraging powerful computational tools. Researchers are using AI and deep learning, specifically convolutional neural networks or CNNs, to automatically recognize and map these features.
What data are they feeding the AI?
They're using high-resolution satellite imagery from platforms like Landsat, Sentinel, PlanetScope, and Maxar. The goal, in collaboration with initiatives like the Permafrost Discovery Gateway, is to produce annual circumpolar maps of these crucial landscape changes.
So AI is learning to spot the collapse from orbit. What about seeing beneath the surface to assess soil moisture, which we know is key to that wet-dry paradox?
That requires moving beyond optical or infrared sensing. We see the potential use of specialized low-frequency radar.
Radar.
Low-frequency polarimetric synthetic aperture radars, or SARs, specifically P and L-band SARs, show promise for mapping water and carbon characteristics within the permafrost active layer soils.
And why are those specific radar bands, P and L band, better suited for the Arctic than conventional optical methods?
Because they use longer wavelengths. Unlike visible light or shortwave infrared, these longer radar waves can penetrate deeper through snow cover, through vegetation, and into the upper layers of soil.
So they can see what's happening underground.
In a way, yes. It allows scientists to map the distribution of water and ice, which is the absolute primary driver of whether CO2 or CH4 is produced by the thawing organic matter. It's essentially a subsurface imaging tool for hydrological conditions.
This impressive data collection effort leads to the final major question. So what does this all mean for forecasting the future, and how is this information being integrated into the next generation of global climate prediction?
It means we are entering a new era of modeling complexity and resolution. For instance, the Permafrost Pathways project is using machine learning for highly accurate upscaling, taking those localized flux tower measurements and expanding them to regional views, developing daily 10-kilometer CH4 fluxes for the entire Arctic.
10-kilometer resolution across the Arctic for daily methane fluxes. That's a huge improvement in spatial detail compared to older models.
It is. They are also running the DVM-DOSTEM ecosystem model at 4-kilometer resolution across the entire Arctic boreal zone. And this model is sophisticated enough to categorize land cover into various specific Arctic community types: wet bogs, tussock tundra, forested areas.
Which is key for the wet-dry paradox.
It's essential. It lets you capture ecosystem-specific CH4 dynamics as different landscapes react differently to drainage.
Looking further out, what kind of computational power is needed to truly capture the global atmospheric transport of this methane accurately enough for policy?
The demand is for exascale computing power. The U.S. Department of Energy's Energy Exascale Earth System Model, or E3SM, is being optimized for these massive next-generation computers.
What's the goal with that?
The goal is to move from older, coarser grids to running the model on a 3.25-kilometer uniform global grid for atmospheric modeling, with the potential for local refinement down to 1 kilometer.
That resolution is mind-boggling. What's the ultimate benefit of simulating the entire globe at that level of detail?
It promises unprecedented accuracy for atmospheric transport modeling. If the Arctic suddenly releases a burst of methane, say a zero-curtain event or a major thermokarst pulse, we will be able to track where that pulse goes in the global atmosphere with far greater precision. This is necessary if we want to distinguish between an Arctic pulse and a tropical pulse and refine our understanding of those critical teleconnections.
This has been a true deep dive into what is arguably the most uncertain and potentially catastrophic feedback loop faced at our climate system. We started by defining the staggering scale of the threat: a frozen carbon bank holding twice the amount of carbon currently in the atmosphere.
We explored the messy, nonlinear science, including the shocking discovery that the cold, dark season accounts for half the annual CH4 flux, and that hydrological paradox where surface drying can, well, paradoxically amplify methane emissions due to subsequent warming effects.
And we detailed the intense multi-platform technological effort required to map it all, from high-precision flex chambers on the ground to CRDS laser analyzers carried by Hercules aircraft and specialized gliders, to the forensic use of stable isotopes that fingerprint the gas source.
Right. And the future of detection relies on cross-calibrating ground data with orbiting satellites and using advanced AI to map the literal collapse of the landscape.
The ultimate takeaway here isn't merely scientific curiosity, it is a point of policy urgency. We established in Section 1 that abrupt thaw affects only 20% of the land but holds 50% of the carbon pool. That massive nonlinear threat is still largely absent from the models used for global climate deliberations.
And to ignore the potential contributions of abrupt thaw and the uncertainty surrounding CH4 in the Arctic, well, it compromises the ability to effectively achieve goals like the Paris Agreement's 1.5 or 2-degree targets.
So what's the message from the scientific community?
The scientific community is unified on this. This latest comprehensive understanding of Arctic carbon feedbacks must be urgently incorporated into climate policy and planning. We need an accelerated, globally coordinated effort to estimate and communicate the likely magnitude of these emissions to inform the increased ambition needed globally. The knowledge is accumulating, and now the policymakers need to operationalize that knowledge.
This complexity in the Arctic, a source we trigger but can't directly control, it raises an important question for you, the listener, to contemplate.
It does. Despite the scientific focus on the Arctic, the long-term rise in methane over the last 40 years is still solely best described by human activities, specifically our fossil fuel and agricultural emissions.
Right.
So if the planet's single largest natural methane source, the tropical wetlands, is now being affected and potentially amplified by climate shifts originating in the Arctic, a process we struggle to control, what additional responsibility does that place on global mitigation efforts for the sources we can definitively control, like fossil fuel and agricultural emissions?
And the source material offers a compelling statistic on that mitigation challenge. The International Energy Agency estimates that as much as 50% of all oil and gas methane leaks could be fixed at zero net cost.
Zero net cost.
It's not just climate responsibility. It's an economic efficiency measure that delivers massive climate benefits immediately.
Something to think about as you contemplate the vast frozen wildcard that is the Arctic permafrost and the immediate mitigation opportunities closer to home.
Thank you for joining us for this deep dive.
Yeah.
We'll see you next time.